Let's set up the parallel force problem. This looks like a static equilibrium problem. We know because we have an object at rest and remaining at rest. So let's start it by drawing what we usually do. The only downside is when we isolate an object for this static equilibrium problem, we don't just have a point like we did before. We've got a big long object with forces all over the place. I am going to isolate the scaffold. So here's the scaffold. And I'm going to draw all the forces on the scaffold. Well, here's what I have. I have a rope A. I'm just going to draw the ones that look pretty obvious. Let's call it B. Let's see what other forces we have. We have the man, 75 kilogram man. Now remember, 75 kilogram man, we have to put forces. So he's roughly here. And we know it's mg, which is 735 newtons. There's a force. We were also told the scaffold is 2,175 newtons and uniform. Newtons is already a weight and it's uniform. That fact tells us one thing. We've always had to draw the weight of the object on our picture. Now we know it has to go at the center of gravity. And since the object is uniform, it goes dead center. We will put some distances in shortly. So dead center, I put the weight of the scaffold, 2,175 newtons. Now look, if we were thinking that this was a force problem, here's what we would do. I'm going to draw my axes for the force problem right here. X and Y. And let's say, hey, static equilibrium, let's do it. Sum Fx equals 0. Sum Fy equals 0. Look at the x equation. Nothing. No x forces. Of course there's 0 because there's nothing to deal with. If we were to set the y equation out by our axes, we would have A minus 2175 newtons minus 735 newtons plus B equals 0. Look at the problem we have. We have two unknowns, and we don't have a second equation for forces this time because all the forces are parallel. We haven't run into this before because previously all of our forces were concurrent. They all intersected at one single point. These are non-concurrent forces. They may cause rotation, and this can occur. So anytime we have an equilibrium problem and the forces are non-concurrent, we always want to start with a torque problem. This will usually help us get through part of these issues. Now, we may have to revisit the force problem later, but we don't want to start with them when we have non-concurrent forces. Because remember, sum Fx equals 0 and sum Fy equals 0 are also true. So let's start with the torque problem. Before we even draw anything else, what does that mean we have to do? The torque problem says this. Sum of the torques equals 0. We can't sum the torques until we find the torques. Here is what I like to do. It's kind of like just a little extra step instead of dealing with forces. I have a picture and a diagram. I have four forces. Each force might cause a torque. We don't know yet, but we're not going to forget them. So the data in the sum of the torques problem is going to come from this little chart I'm going to make. Torque is plus or minus force times lever arm. And what I'm going to do is list each one. I could have a torque due to A. I could have a torque due to the 2175 Newton weight. I could have a torque due to the man. And I could have a torque due to rope B. It's called I could. Let's see what happens when we get there. Well, we've got forces for each case. And in fact, we could write through all the forces right now. Here's the force. Here's the force. Here's the force. Here's the force. We just need lever arms for each of the forces. So with torque problems, we know the forces every time. All we have to do is find lever arms. Now look in this one, we've got a problem. If we want a lever arm, we need a pivot. This is a scaffold. There is no actual pivot point here. There's no place where this is designed to spin around, which is probably good, because if you decided to make scaffolds that were designed to spin, you probably wouldn't sell one, because they would be death scaffolds. But this is a technique we can use when no actual pivot point exists. If there is an actual pivot point, we will use that as the pivot. If there is none, this is just a thought exercise and we can figure out what to do. We know the object is in equilibrium. It's true. It must be in equilibrium. Therefore, all three equilibrium equations are true. If they are true, let's examine the torque one. This sum of the torques is 0 doesn't say about just this pivot or just that pivot. It says the sum of the torques are 0. So that means if I pick any point on this object and pretend there is a pivot there, if the object is in equilibrium, the torques must sum to 0 about that pivot. For torque problems, you are allowed one and only one pivot. And the goal is to make a pivot, choose a pivot, to make one of the unknowns go away. Well, we've got two unknowns, A and B. So here is where I'm going to choose a pivot. One more time. If you have a physical pivot, if there's an actual hinge, you must choose the hinge as the pivot point. We'll see that in another problem later. Since there is no hinge here, a logical place to choose a pivot would be either where A or B intersects the bar. I am going to choose my pivot here. This is a choice. No pivot exists there. I'm pretending one. Now, once I do that, the torque due to A about that pivot is 0, not because the force is 0, but because the lever arm is 0. Once I do that, now for the rest I'm going to draw some distances in. There's lots of ways to draw distances. You could draw them off from the pivot, or in this case I know distances between each force because I know the 2,175 Newton force is dead center, which means it's at 3 meters in. So let's draw the distances that were given. Here we go. This was given as half a meter. This is given as half a meter. And this was given as 1 meter. Well, everything's got to add to 6 if you go between the forces. So that means this is 2.500 meters, and from here to here, that line is 1.500 meters. So now we know the distances, and now we can calculate torques. So let's use the 2,175 Newton force, find the lever arm. Perpendicular distance from pivot to line of action. So look it, here we go. There's the perpendicular, it's 2.5 meters. It's going to make it rotate clockwise, so it's negative. So we can multiply that out, we just have a number right there. We can now find the lever arm for the 735 Newton force. These go relatively quickly. The lever arm is the length from here to here. Well, that's 4 meters. Remember, perpendicular distance from pivot to line of action. That'll make it rotate that way, which is negative. Well, here's the force B. The lever arm all the way across, that's 5 meters. Must be positive, it'll make it rotate the other way. So look at what we have. We have 3 torques that we could multiply out. Okay? So let's sum them up. The first one, the negative 2175 newtons times 2.5 meters. And we will get negative 5437.5 Newton meters. Let's just keep all the figs for now. Negative 5437.5 Newton meters. The second torque, where the 735 is, negative 2940 Newton meters, plus 5 meters times B equals 0. There's our torque equation. The hard part is calculating the torques. The easy part is shoving them in here. So now we can solve this. When we do, we get B equal to 1676 newtons. Because when you divide by the meters, you will get newtons out. This is B. Quick check. it needs to be positive. We are finding magnitudes. Now, how do we get A? Well, we didn't use the sum Fy equals 0 for nothing. We do not want to solve the problem all over again by choosing a pivot at B. Again, the rule is make one pivot. Well, now what am I going to do? If I take B and go way this way and shove it in over here, I can solve for A, and I will get 1, 2, 3, 4 newtons. Another check. It's positive. And here's another quick check. The man is standing closer to B, so the tension in B should be larger than A, and that's what we got. So, in summary, for parallel force problems, many times if no pivot is given. Now, some parallel force problems do have a pivot given. You must choose the hinge or the pivot when it is. But if there is none, you get to choose one. Because if the object is in equilibrium, the sum of the torques must equal 0 for any and all points chosen to act as pivots.